Welcome to the final submodule, number 4 of 4, on Drillstring Design. In this section, we will focus on buckling behavior, design principles, and practical methods to reduce risks during operations. This session builds on the earlier modules, bringing together mechanics and field practices to complete our understanding. In this module, we will concentrate on drill string buckling and related design principles. First, we will define what buckling is and how it develops in tubulars under compressive loads. We will then look at the different forms of buckling, namely sinusoidal and helical, and examine the conditions that cause a transition from one form to the other. Understanding these modes is essential because they directly impact drilling performance and equipment life. Next, we will review factors that influence buckling, including axial load, well inclination, pipe stiffness, and borehole clearance. We will then explore the Dawson-Pasley formula for critical buckling load, which gives us a practical method to evaluate when drill string buckling is likely to occur. Building on this, we will consider common field practices and tips to prevent or control buckling during drilling. The module also covers buckling behavior in inclined and curved well bores, an increasingly important consideration in directional and horizontal drilling. Finally, we will apply these concepts to drill collar and drill pipe selection before reviewing casing wear caused by buckling. By the end of this sub-module, you should be able to recognize buckling risks, perform calculations, and apply preventative strategies in real operations. Buckling design addresses the structural stability of the drill string under compressive loads. When axial forces exceed a certain threshold, the drill string can deform into sinusoidal or helical shapes. This section introduces the problem of buckling, its consequences for drilling, and the methods we use to design against it. Buckling in a drill string occurs when compressive forces acting along the pipe exceed its capacity to remain straight within the well bore. Unlike simple tension or torsion, buckling is a stability problem. Even a relatively small increase in axial load can lead to large lateral displacements once the critical load is reached. In practice, buckling starts when weight on bit and the weight of the collars impose axial compression on the drill string. If the applied force is greater than the critical buckling load, the pipe begins to deform. Initially, this deformation appears as a sinusoidal wave, where the pipe gently oscillates against the borehole wall. As the load increases further, sinusoidal buckling transitions into helical buckling, in which the pipe coils around the borehole wall. This helical shape greatly increases side forces, contact stresses, and friction. The largest stresses occur when buckling in rotary drilling. When sliding, there is usually no structural damage, but it does impair weight transfer. In summary, buckling is a critical design consideration because it reduces efficiency, damages equipment, and increases operational risk. This slide illustrates the two primary forms of drill string buckling. On the left, we see sinusoidal buckling, where the pipe forms a gentle wave pattern within the borehole. This usually occurs at lower compressive loads and results in moderate sidewall contact. On the right, the image shows helical buckling, where the pipe coils against the borehole wall in a spiral form. This transition occurs at higher compressive loads, causing significantly greater side forces, higher torque and drag, and accelerated wear. When drilling a 6-inch horizontal hole, it is not uncommon to mistake a helical buckling issue for a hole cleaning issue and end up performing a wiper trip. In these situations, you need to slack off the weight and increase the RPM. Understanding this progression is important because it helps us anticipate the consequences of increasing compressive loads. This slide shows a photograph of drill pipe that has buckled inside the well bore. Notice how the pipe has deformed into a series of bends rather than maintaining a straight profile. This deformation is the direct result of compressive forces exceeding the pipe's stability limit. Once buckling occurs, the pipe pushes repeatedly against the borehole wall, creating high side loads, friction, and wear. In severe cases, the pipe can lock into a helical shape, making it very difficult to move or rotate. This image demonstrates why buckling is a serious operational concern that must be addressed in design. Now let's examine the factors that influence drill string buckling. The first is tension. This comes from several sources: the weight on bit, the buoyed weight of the string below the point of interest, axial drag as the pipe moves, and also hydrostatic pressure acting on exposed areas of the pipe. All of these combine to either stabilize or destabilize the string. The second factor is what we call inherent stability. This depends on the geometry of the hole and the pipe itself. Hole size, inclination, and the magnitude and direction of any doglegs are key. We also need to consider the pipe's stiffness, expressed through its moment of inertia, and the clearance between the pipe or tool joint and the borehole wall. Material properties such as Young's modulus and the buoyant weight of the string in mud also play an important role. Finally, we have stability forces. These are non-axial pressure area forces caused by pressure differences acting across the pipe. The net force is expressed as internal pressure times internal area minus external pressure times external area. Depending on the balance, these forces can either help resist buckling or increase the risk of instability. The Dawson-Pasley formula is one of the most widely used methods for calculating the critical buckling load of a drill string in an inclined well bore. It provides a practical way to estimate when sinusoidal or helical buckling will occur, based on the balance between pipe stiffness, weight, clearance, and inclination. In simple terms, the formula shows that buckling occurs when compressive forces exceed the pipe's ability to resist lateral displacement. The bending stiffness, represented by the product of the modulus of elasticity and the area moment of inertia, provides resistance to buckling. On the other side, the effective compressive force depends on the submerged weight of the pipe, the inclination angle, and the radial clearance between the pipe and the borehole. What this means in practice is straightforward. As inclination increases, the critical buckling load increases, making buckling less likely. Similarly, larger borehole clearance lowers the threshold, while stiffer, thicker-walled pipe raises it. Engineers use this formula to decide whether a given drill string configuration will remain stable under expected loads. By applying Dawson-Pasley, we can identify potential instability before operations begin and make design adjustments such as using heavier collars, reducing weight on bit, or altering well trajectory. Here are some key guidelines for preventing or mitigating drill string buckling during drilling. The most important practice is to control weight on bit. Excessive weight greatly increases axial compression and accelerates the onset of buckling, especially in deviated sections. Another strategy is proper stabilizer placement. Stabilizers provide lateral support to the string, reducing unsupported lengths and thereby raising the critical buckling load. Drill collar selection also matters. Heavy, stiff collars placed low in the assembly help carry axial load and reduce the risk of buckling in the drill pipe above. Similarly, using heavyweight drill pipe as a transition zone between collars and regular pipe helps distribute forces more evenly. Operational practices are equally critical. Avoiding sudden increases in weight or torque, monitoring drag and rotation resistance, and using torque and drag models all help detect early signs of buckling. Fluid buoyancy can also be managed by adjusting mud weight, which alters the effective submerged weight of the string. In essence, buckling prevention requires a balance of design and operation. By carefully planning the BHA, optimizing stabilizer placement, and controlling loads, engineers can reduce the risks and consequences of buckling. In inclined and curved wellbores, buckling is an important concern for drill pipe integrity. When the drill pipe lies against the borehole wall, the wall provides lateral support, which increases resistance to buckling. This stabilizing effect is most evident in curved sections, where side forces act to keep the pipe constrained. To better understand buckling, we can divide the borehole into three main sections, from surface down to the kickoff point, KOP, where the well remains vertical, the build section where curvature is introduced, the tangent section at an angle above 0 degrees, where the wellbore maintains a constant inclination. Interestingly, the pipe tends to be more stable in the curved build section due to constant wall contact. Therefore, buckling analysis typically focuses on the vertical section down to the KOP and the tangent section, as these are where critical instability risks are the highest. The implications of buckling are severe, including higher torque and drag, casing wear, and the risk of stuck pipe. Therefore, engineers use predictive models and software to evaluate buckling loads under specific hole sizes, pipe weights, and mud systems. The top graph shows the critical buckling load in inclined straight hole sections. The y-axis represents critical load in thousands of pounds, while the x-axis is hole size. The curves show how buckling resistance increases with increasing hole angle. For example, at 60 degrees, the pipe supports much more load before buckling compared to a vertical hole. The lower graph compares build and drop well bores. Critical buckling load increases with build drop rate, and the pipe is more stable in building sections blue curves compared to dropping sections red curves. Engineers use these charts to assess safe operating loads. Drill collar selection is critical because it directly affects weight on bit, directional control, and buckling resistance. Two key factors govern drill collar performance: weight and stiffness. Usually, the largest outer diameter OD collar that can be safely run is the best choice. A larger OD provides more weight for weight on bit, which improves bit penetration efficiency. It also increases stiffness, reducing the risk of buckling and helping to stabilize directional tendencies. Additionally, larger collars reduce cyclic motion because they fit the hole more tightly, which minimizes vibration and improves toolface control. Another important design principle is keeping the bottom hole assembly as short as possible. A shorter BHA reduces rig handling time during makeup, which improves operational efficiency. They also reduce the number of connections, lowering the risk of weak points in the drill string. Moreover, minimizing the total number of drill collars in contact with the wellbore decreases the risk of differential sticking, a major non-productive time issue in drilling operations. Ultimately, selecting the correct drill collar size is a balance between mechanical stability, operational efficiency, and risk mitigation. Drill pipe selection follows similar principles to drill collars, with weight and stiffness being the governing factors. These properties determine how well the pipe can transmit torque, carry axial loads, and withstand operational stresses. In practice, the preferred option is usually the drill pipe with the largest outer diameter OD and inner diameter ID. A larger OD and ID minimize pressure losses along the string, allowing more efficient hydraulic power to reach the bit. This improves bottom hole cleaning and drilling efficiency. When selecting drill pipe, engineers must also consider several critical requirements. First, the pipe must be able to drill to total depth and support the full bottom hole assembly weight. Second, it should provide adequate overpull capacity, enabling operators to free stuck pipe if necessary. Third, it must resist both burst and collapse loads caused by downhole pressure fluctuations. Additionally, drill pipe must withstand torsional stresses, particularly at tool joints where stress concentrations are the highest. Finally, pipe selection must account for harsh environments, such as hydrogen sulfide H2S exposure, where sour service grades are required to resist sulfide stress cracking. Proper drill pipe selection ensures operational safety, mechanical efficiency, and cost control. Casing wear is a long-term integrity issue caused by continuous contact between the drill string and casing. Several factors influence the severity of wear. The first is side forces. Wear is most pronounced at low dogleg severity sections where the pipe tension is greatest, creating higher contact forces against casing walls. High tortuosity should be avoided because it increases irregular contact and accelerates wear. Additionally, casing buckling must be prevented as it creates concentrated points of stress. Drill pipe protectors can be fitted to reduce direct metal-to-metal contact, extending casing life. The second factor is the wear factor, represented by casing wear models. Pipe hard banding, especially smooth flush types, is often applied to reduce abrasive action without cutting into the casing. Finally, relative motion between pipe and casing plays a major role. In this last submodule, we explored the fundamental aspects of drill string design, beginning with failure modes. We examined how drill strings can fail due to fatigue, overtension, torsional stresses, or buckling, and highlighted the importance of anticipating these risks during design. We then reviewed the criteria for selecting drill string components. Drill collars and drill pipe must be chosen not only for weight and stiffness, but also for their ability to transmit torque, support the bottom hole assembly, and resist burst, collapse, and sour service conditions. These choices directly impact drilling efficiency and operational safety. A major focus was on buckling. We differentiated between sinusoidal and helical buckling, discussed the Dawson-Pasley model for calculating critical buckling loads, and examined how inclination and wellbore geometry influence pipe stability. Practical tips, such as maintaining the neutral point in drill collars and using engineering software to model each BHA, were emphasized. Finally, we considered the structural soundness of the drill string, including casing wear. We saw how side forces, relative motion, and wear factors impact casing life, and how protective technologies like smooth flush hard banding and drill pipe protectors can mitigate damage. Together, these elements provide a complete framework for safe and efficient drill string design. This concludes the final submodule on drill string design. I hope you got value from this. Please proceed to the quiz. Thank you.